Perfect. So yes, guys. In previous video, we talked about introducing an integrator in order to do the noise shaping. So the phenomena of noise shaping is basically based on the noise transfer function. So we talked about it, we derived the function. So the signal transfer function comes out to be 1 because we need the signal as it is. And the noise transfer function comes out to be 1 minus z inverse. And we also saw that after the integrator is followed by this quantizer. So the quantizer is represented like this, which is an additive noise source. And it obviously has a delay. So we also looked at the curve of the NTF, and when we evaluate it at infinity, so it goes to 2 at infinity, and at DC, where z equals to 1, it faces infinite attenuation. So basically, it is 0. So then we also said that we talked about the spectral density and we talked about the magnitude of NTF. So at lower frequencies, the magnitude of NTF comes out to be omega. And then we integrated the in-band noise because first, if we integrate the whole noise, then we saw that the noise, so at this stage, I mean, yeah, at this stage, the noise comes out. So yeah, we need to talk about that point here. Okay. So basically, when we integrate the in-band noise from 0 to pi by OS R, so then we got delta square by 36 pi times pi cube by OSR. So if yes, here we say that if OSR goes up by a factor of 2, so basically if we double the OSR, the in-band noise will reduce by the factor of 8, which is the noise will reduce by a factor of 9 dB, and which is basically representing 1.5 bits increment in the resolution. So definitely we seem to be doing better than blindly low pass filtering the oversampled signal where we got the where we got 0.5 bits increment for every doubling of the OSR. So we also looked at the impulse response, and we saw that for NTF, the 0 is at z equals to 1 and the pole is at z equals to 0 based on this transfer function. And basically, we saw the phenomena of noise shaping. And then we said that, okay, at this point, basically, when we are looking at the NTF or the noise transfer function, so basically this is something which we will get in time domain. So basically we have an impulse response of NTF sequence in time domain, and it has 1 and it has -1, and all of the samples are 0. And the thing is that the sum of the samples of impulse response of a NTF must be 0. So why should be 0? Because if we evaluate NTF around DC, so basically at z equals to 1, it comes out to be 0. And that means the magnitude is 0 at DC, or basically at z equals to 1. So therefore, the sum of the samples should be 0. And if so, basically, if we have a NTF, I mean noise transfer function, so then for this noise transfer function, the inverse transform of NTF of z is denoted by h of n. So basically, the z inverse of NTF of z is given by h of n. Then basically, summation of h of n, where n goes from 0 to infinity, should be 0. So this is what it means mathematically. And then we said, okay, we'll apply, we'll implement it in a block diagram. So we saw this block diagram where we have the input, then we have the difference over here, and then we have a first order transfer function And we all are aware about this transfer function, that to see the phenomena of noise shaping, we have a very high gain at low frequencies, but the gain drops as the frequency increases. So basically, the gain drops as the frequency increases, and um, basically, we are facing, I mean, the noise transfer function will be facing the maximum attenuation around DC, where our input signal hovers around. So basically, we are pushing the noise outside the required band of interest. So then we have a quantizer, and after quantizer, we say that at this point we have a noise which is in band, and then when we smooth out, or when we use a decimation filter to smooth out, or basically to do a low pass filtering, after that we get a very high resolution signal, and this is a technique of showing a lower bit converter to be a very high resolution converter. So basically, we have a poor converter. I mean, we have a converter with, let's say, 2-bit converters, and we are showing it as a higher bit converter using the technique of oversampling, quantization, and noise shaping. I mean, oversampling, quantization, and then filtering out the process using a decimation filter. So then let's talk about the power of the noise. So basically, at A, or maybe at the input, we have the power of noise, which is spreaded evenly throughout the broadband of, let's say, all the bins, or let's say throughout fs by 2. So we have delta, or throughout pi. So we have delta square by 12 pi. And then we have the magnitude of the noise, right? So we have derived this over here also. So we talked about 0 to pi by OSR. So we integrated this noise. So what about this complete noise at this stage? So we talked about the noise. So we talked about the noise at this stage, and we derived it, and we found out that it is very the noise is very low, and it is pushed away at higher frequencies. But what about at this point? I mean, at this point, we have delta square by 12 pi, but then we will integrate it from 0 to pi. So we'll integrate it from 0 to whole pi. Okay. So we have delta square by 12 pi, and integration of 0 to pi, magnitude of NTF square times, it's a function of frequency. So, but we know that, I mean, from here, we know that 1 by pi times, if we integrate from 0 to pi, the NTF square comes out, basically is corresponding to summation of h square of n, where n goes from 0 to infinity, and this gives us a value of 2. So then the mean squared value of noise at B is in fact greater, I mean, at this point after quantization, is in fact greater than what we had without noise shaping. And in this particular case, it is 2 times. Why? Because we have delta squared by 12 pi multiplied by this, and this comes out to be 2. So we have 2 times delta squared by 12 pi. So initially we had a noise, but while achieving the phenomena of noise shaping, the output of our, let's say, delta sigma converter is having a very complicated noise. But then when we use a decimation filter, everything filters out very smoothly, and we have our input signal, which is very high resoluted, or basically of very high resolution. So even though like the noise is getting complicated, but we are pushing that noise away in higher frequencies. So we are getting very better quality of resolution, because anyway, I mean, like, if even though if the noise is increasing, it's not going to bother us, because anyway, after the quantization, we are doing the decimation filtration, or we are smoothing out. So but we need to talk about the noise, what happens at B, because later on when so this is first order delta sigma, where we have the difference over here. So this is delta, and this is the integrator, right? So we have sigma. So basically, we are leading to a delta sigma, and this is a first order delta sigma. But when we talk about higher order delta sigmas, then at point B, we will see very complicated structures for noise, but that's not going to bother us because in the end we are going to have a decimation filter. So then when we represent it in a linearized model, so the quantizer is the one who is the most non-linear. So we linearize it by realizing the quantizer as an additive noise source. And if we want to find the impulse response from the quantization noise port to the output port. So forget about the loop as of now. If we have given a box and let's say we have given a box and we have told that, hey, this is your, let's say the converter. So then you have two input ports, which is U of n for the signal and for the noise, and you have one port for the output. So if we would have had asked to find the impulse response from quantization noise port to the output port, right? Then what we do is basically we inject an impulse at the noise port. So let's say this is one impulse, right? So we inject it at the noise port, and at the output port, we check for the impulse. So for the very first sample that comes out of the output port must be this, I mean must be one, or the impulse which is injected. So why? Because rest of the feedback. So rest of the feedback will see the impulse in the next cycle of clock, because we are dealing with samples. It's not a continuous domain anymore. So there will be a delay from the quantizer itself. And due to that delay, the whole feedback will see this impulse after, I mean, after one cycle of the clock, or basically next cycle of clock. So, but when we talk about that particular clock, so the first sample that comes out at the output port must be 1, or basically the impulse which is injected, regardless of whatever the transfer function we have over here, because this will be activated after the delay. So mathematically, h of 0 should be 1, and that should be regardless of what transfer function we have for the integrator, or basically for the noise shaper. And h of 0 corresponds to NTF evaluated at z equals to infinity. So as we know, NTF of z is basically h of 0, h of 1 z inverse, and so on till infinity. So basically this concept in books is called having no delay free loops. And basically for a delta sigma modulator, one of the sanity check is we should make sure that when we design a delta sigma, so we evaluate the noise transfer function at z equals to infinity, and we must get 1. So then, I mean, as we have discussed up till now, so there are, I mean, this is the structure. So we have, like, let's talk about the delta sigma modulator. So this is a delta sigma modulator where we are doing the difference. So this is delta, and over here we have the integrator. So we have sigma, and I mean, in the books, it's presented as the input is given by U, the output of the integrator is given by Y, and the output of the delta sigma modulator is given by V. And at this point, so basically, we analyze this for a first order, right? So if you guys remember, when we had no integrator, then for every doubling of OSR, we got a increment in resolution by 0.5 bits. But when we introduced one integrator, so over here for the first order, we got increment in 1.5 um, resolution. So 1.5 bits of resolution we got for every doubling of OSR. Maybe what if we use two integrators or we use nested compensations, let's say feed forward, or let's say Miller compensations for nested op amps. So then we will get even more, I mean, you understand what I mean, right? Even more higher resolutions. So once we have proved this, then we can go for higher orders. So this is basically represented by some function which is function of, I mean, L of Z. So then this, we replace this with higher order transfer functions for more advantages. And the delay over here is basically pushed into this block. And this block is basically called as loop filter. So, and one may say that why should you and V, so basically this is V, right? Coming from the output as a feedback. So why should U and V should see the same transfer function? So then we say that to elaborate more, so this is the loop filter where we implement um, higher order transfer functions. So then we have input, which will give us L naught of U, and we have this feedback, which will, and obviously we need it in inverse. So which will give us minus L1 of V. So we have these two transfer functions over here, and then at the output we get Y, and after the quantization we get output as V, and the delay is pushed into this block, which is loop filter. So then when we represent it in a linearized model, so the quantizer is represented by additive noise source. It is given by E, and we have L of Z. So this is the linearized model for delta sigma modulator. And we know the signal transfer function is basically L of Z by 1 plus L of Z, and the noise transfer function is 1 upon 1 plus L of Z. And basically the output V is given by the signal transfer function times its, I mean, its resemblance, which is U of Z, and the noise transfer function and its E of Z. So this is a delta sigma modulator, and we can see this, I mean, we can plot for the same. So initially this is the case. So in this case we blindly oversampled the signal and shaped it. So but so basically this is the quantization for oversampling only. But when we use a sigma delta, so the noise, I mean noise at higher frequencies, so this is not passed through a decimation filter yet. So this is the output of delta sigma, and we have a complex noise. But I mean, when we shape it off, so basically when we zoom it, I mean when we zoom this in, so we have this case where we have oversampling only. But then in the case of first order delta sigma modulator, we have this behavior of noise where the noise is complicated at higher frequencies. But when we shape it out, then the resemblance to the original signal is even higher. So the resolution is even higher. So this is what I meant when we talked about the theory. And then obviously this is the noise before filtering. So this is the case where we had only oversampling, but then this is a noise before filtering in the case of delta sigma modulation. And then when we filter it out or when we smoothen it out, so then the noise has very less magnitude, or the noise is reduced very significantly and smoothly. So this is what I talk about. So this is what a delta sigma modulator is. And we have covered the first order delta sigma modulator, and will now from this point onwards we'll dig and dive deep more into this delta sigma, and we will analyze it analytically and quantitatively as well. So from next video onwards, we'll dig more into delta sigmas. So that's all for this video from my side. Thank you so much. And if you have doubts, let me know.